So hello everyone, hello again. I'm Shang, second year PhD student supervised by my tutor working on reinforced learning in chip design, so particularly for placement problems. So I roughly divide this talk to the two parts. So the first part will be the general introduction of the chip placement and how reinforced learning apply to it. The second part is a discussion, the challenges of the reinforced learning in chip placements. So I specifically set the question sessions between two parts and in the end. So I would really appreciate if you can ask the questions in your question sessions. So in this talk, there are three short terms will be frequently mentioned. The first one is RL. I guess you guys are already pretty familiar with it. It's the reinforced learning. So second one is IC, means integrated circuits, or you can think as the chips. And third term is EDA, electronic design automations, or you can think as chip design. So the goal of my tea time talk is for introducing this interesting, challenging, and promising reinforced learning applications, and also discussing the challenges of the applying reinforced learning in this domain. After listening to this tea time talk, I hope the audience can know how reinforced learning applies to chip design and can think RL in chip design is really cool. And even further, I hope you guys can even willing to experiment your RL cells on chip design. So please don't worry about this graph looking complicated. So you don't need to understand all those details right away. So we will go through it together and only focus on one part. So this diagram roughly summarizes the chip design and the manufacture procedures. So in the past 60 years since the birth of the chips, the IC industry had a complete and virtual industrial procedures. So with the development of the AI, more and more machine learning and AI technologies show in this process. So like large language models, reinforced learnings. So but today, we only focus on the placement part, especially how to using reinforced learning to solve placement problems. So what's the chip placement problems? At a high level, it's just a form of the graph results optimization. We take as input a graph the chip components, like memory components, macros, logic gates, like AND, OR, NAND, NOR, all of which are connected by wires. The objective is to place this graph onto a 2D chip canvas such that we minimize various costs like the wear length, latency, power consumptions. Those metrics may be conflicted to each other. So it's a multi-objective optimization problem while adhering some constraints like routing congestions and cell utilizations. Since the birth of chips, the engineers have been researching this problem for a long time. So the placement algorithm also iterated itself. So in the early beginning, so before the 1980s, so they mainly used the partitioning-based method. Just like the name, following the divide and conquer strategies, engineers split the circuit into sub-circuit and solve the problem one by one, like the min cut. And then moving to the 1980s to 1990s, simulated annealing methods start to dominate. It's iteratively improved the placements by making local changes. So after 1990s to right now, analytical solvers become the backbone algorithms. Analytical-based methods formulate the problem as the continuous optimizations and solve it using technique like quadratic programming or direct gradient descent. So drain place is the current state-of-the-art algorithms, and the commercial EDA tool also build their own placement algorithms based on the drain place. So all these methods are pretty good or even efficient in some ways. So I won't say they are bad or say they are awful to highlight how amazing of RL method is. But sometimes, so this method, particularly analytical method, must relax the non-overlapping constraints to have the solutions. So those the analytical placers will produce the result that the electronic components are overlapped each other, which cannot be manufactured. From 1980s to 2020s, the number of the blocks in chips increased from hundreds to 10,000 or even more than 10,000. So with the growth of the modern chip scale, the phenomenon has become increasingly evident. So the human engineers have to evolve to fine-tune this unqualified floor plan or just the hyperparameters of the placement solvers until they can get the qualified results. So these iterations may take several weeks. So it's really time consuming. So along with the development of the chip design skills, the researchers start to look for more effective placement methods. So they move to the learning-based methods, particularly for RL-based methods. And the Google in 2020 published a Nature paper about applying reinforcement learning to solve chip design, so which totally shocked the whole EDA domain. So Google trained the agent to place the blocks one at a time onto the canvas. And after placing all those blocks, the agent received the reward in end of the episode. So the state space will be the graph plate embedding of the netlist, embedding of the current block and the canvas. The action space is the number of the grid cells, and reward is the weighted average of the virulence, density, and congestions. So that's the whole thing looking like. In the early beginning, so the board is empty. So, and then the agent decide where the first block should be placed, then the second block, the third block, and so on. Once finishing the whole placement, agent can get the different metric performance from the simulator, like the virulence, congestions, densities I mentioned in the previous slide, and that's also metrics weighted sum as rewards. Google claimed that on TPU design, their RL agents trained 24 hours can achieve the same performance made by human who takes 6 to 8 weeks. So notice that 24 hours is including the agent training time from the scratch. So for the third comparison, the human takes several years to become the chip engineer expert. So when you think the RL agent speed up the whole procedures by several years, so you will say what amazing of RL is. And Google's work proved that besides a virtual game like a Go, chess, StarCraft, the virtual game environments, RL can definitely show its power in real problems. So I will explain why these measures are blurry in NASA sessions.
Questions? So you had a word violation here. Is that really bad or just like a soft violation?
What's the meaning of violations?
It can't be manufactured or that it isn't all.
Oh,
violation sounds like a very bad.
oh, yeah. So I think I don't know what's the real metrics meaning in here. So that's 1070-66 is the really good or really bad for the chip in the chip domains. But I will say, so no matter how much the violation is mixed, so it's not too much difference compared to the human expert made and the machine learning the RL agent made. And the most important is, so the speed up is 6 to 8 weeks to only 1 day. So yeah, it's still the big improvement.
But this should actually continue manufactured.
Yes, exactly.
What word violation isn't that bad?
Yeah, maybe, hopefully. So I will explain more in the next sessions. So Google set off the new wave of the reinforcement learning in chip placements. So in 2021 Europe, this paper introduced the random network distillation, aka RND, as the intermediate reward to encourage agents to explore the state space. In 2022 Europe, this paper proposed a new state representation, which is not required graph learning anymore. In 2023, at Clear, this paper proposed to include field expert data in Ripley buffer to boost the agent's performance by using off-policy learning. So in 2024, as EA, we proposed the first reinforcement learning-based algorithm to solve the FPGA placement. So more and more AI researchers start to apply the various RL techniques to address the chip placement problems. And more AI researchers start to notice that chip placement is one more promising RL applications. So before I move to the next sessions, so any questions in here? Go ahead.
Yeah, so you on the previous slide you had like the different other papers, but you mainly talked about kind of one MVP for how you can like look at chip placement. In these other papers, was it a similar Markov decision process that they used, or did they consider something different?
Oh, that's really nice catch. So I will mention that in the next sessions. Yeah. So the short answer is yes, they're all using the same MDP framework. Yeah.
So how big are the boards that they use in these papers? If I'm thinking of it like a game, using something like 11 by 11, this is 100.
Yeah, exactly. Yeah, it's just like the 10 times 10, 11 times 11, or 100 times 11, 100 times 100. So just like the Go board. Yeah. Okay. So due to the confidentiality, Google never released their data set, which is a TPU design. So that's why that image are blurry. So that's also the maybe one answer to the Ross questions. So I also don't know, do they really solve this problem? Are they really manufactured? Because the Google never answered that. So since the EDA people was totally shocked by the Google claim performance, so lots of researchers, engineers put efforts to reproduce Google's results. So unfortunately, they all failed. Andrew Kahn, the famous EDA professor, led his team to do the reverse engineer for whole years to the Google's work and published the paper on top EDA conference about assessment of the Google paper. And Igor Makarov, another famous EDA professor, published the paper with very, very harsh critic to judge the Google paper. And Nature also started investigations on the performance claimed by the Google. So obviously, today's tea time talk purpose is not including embarrassing Google. So as the R person, I come here to discuss, so what's the challenges we face to when applying reinforcement learning in chip design and how we address those challenges. So I will discuss those challenges. Some of them I have the solutions, but some of them I don't have. So I welcome everyone tell me yourselves and join discussion in the end. So expert data is really hard to access. So for EDA domain. So EDA domain prefer to close source instead of open source. Those commercial EDA company treat their expert data and chip engineer, much like the golem in the hobby, treat the Lord of the Rings. So for the solution of this challenge, I don't have any solutions right now. So, but maybe the reinforced learning is one solution compared to the data-hungry supervised learning. I will explain why I mentioned supervised learning in the next slide. So our previous work, including ours, are restricted to one framework that placing blocks one at a time. But this MDP is super counterintuitive, since we only care the final placement results and not care how the agent achieved this final placement results. So quite different from the Go game. So where a player can only take one move before the opposite unknown next move. Chip design, chip engineers have the whole information of the 13 net list and rarely need to do the floor plan in a sequential process, one block at a time. So chip placement problem may more suit to the regression predictions, since we don't care the intermediate placement procedure, but due to the limited expert data set, it's really difficult to train one supervised learning model to predict these placements. So we for solutions for that one. So we proposed a new MDP, the swapping blocks one at a time. So the agents make the adjustments based on the initialized placements and improve it step by step. So compared to the MDP placing blocks one by one, the agent has a holistic view at each steps, and the agent can receive the rewards from the simulator more frequent. And the third challenge is the state space is super huge. So exhausting all possibility for chip placements is one permutation problems. The state space will increase exponentially along with the increasing of the number of the blocks. So compared to those famous challenging RL game environments known for the huge state space, like a Go, the real chip state space is way much larger. And the number of the state space will be 10 over 9,000 when placing 1,000 blocks. And the real chips may easily have the thousands or even 10,000 blocks. And so notice that the Google's works only plays around 100 blocks. So compared to the reality settings is way much less. So this huge search space further highlight the sample inefficiency of the model-free RL. So our solution is, so maybe we can try to using the model-based RL methods like AlphaZero, Mu0, and we do have the transition model, and the Monte Carlo tree search is more efficient in large state space. So besides, we can also introduce the human heuristic to narrow the search space. So number 4 is the imperfection of the reward settings. The first one is the reward misalignment. So in old MDP, placing blocks one at a time, the agents will only receive the numerical feedback in the end of the episode. So in this MDP, the agent has no idea each move's performance. So for example, the agent received the poor score in the end of the episode, but it may confuse which steps it makes the wrong moves. So our solution is, so because we already proposed this new MDP, so we swapping the block one at a time, so which the agent can receive the reward at each steps. So reward misalignment is automatically fixed. And another challenge is in the imperfection of the reward setting is the multi-objective optimizations. So our all reinforced learning in chip placement paper mainly optimize the variance or use the weighted sum as the rewards. But the chip placements is the multi-objective problems. So in reality, the human engineers require the flow plan to reach some certain performance in variance, meanwhile reaching the certain performance in congestions, and also only consuming such amount of power as well as taking such amount of cell areas and etc. So there are so many metrics and there are so many performance they need to achieve. So there is no meaning for realistic setting to do the single objective optimizations. And all rewards using those papers are the proximate reward from the simulator. That rewards are correlated but different to the real performance that human engineers really care about. But that real performance can only be accessed by the commercial EDA tool, which it takes 20 minutes or even longer to evaluate the performance for the agents. So it's a really time-consuming for agent to ask. So for the last two imperfection reward settings, so no real rewards and the multi-object optimizations will be the open discussions. So let's come back to review those 4 challenges. So we may find those challenges may not only exist in chip placement problems. So it may be the challenges for all our real world applications. So first, so not only in EDA industry, but all industrial applications, the label data set is expensive to acquire. The commercial company treat the data as the valuable capitals. And secondly, not all real world problems have the temporal features required by MDP. So the existing MDP formulation for that real world problems may be imperfect. And thirdly, the real world problems often have a huge search space compared to the real world Atari games. So they need more efficient searching algorithms. So last, how to perfectly construct a reward function is indeed the tough and challenging problem, just like the last Tuesday tea time talk presented by my lab mate Caddies. And in the end, so thanks for everyone for listening and welcome to join the discussions. Go ahead, Ross.
Well, down on that last point, I've been very interested in finding the reward function so we can have as well. Your answers aren't that good. I guess they're not. There's multiple different objectives, and you're saying here's when an expert, human expert gave, here's what I gave. I guess you can show they're dominated, but they're not dominated. Maybe you got a better answer. How do you know you didn't have a good? Just comment on what is the real goal?
Yeah, that's a really good point. So I think so first, so it's a really under discovered for this research, applying reinforced learning on this or multi-object optimizations on this chip domain. So maybe it's indeed really require lots of human experts to tell you what thing you really need, and there's no clear solutions or metrics to tell the agents or maybe our RL researchers which one is the best, which is the optimal solutions.
My current philosophy is if it's a human to tell you the answer, then it's not really interesting. There's really some objective measure you're trying to optimize. You're just trying to match a human, while humans disagree which one you're going to match.
Oh,
I bet the kappa score is not one, there is disagreement.
yeah, that will be another open discussions. Yeah, so maybe so if I understand right, it's just like maybe the agent coming up with the floor plan that human engineer may not disagree with that. So
that one didn't, but these three did.
what's mean which we did?
And there might be different human. I work in medical applications. And the kappa score, kappa is a measure of how much experts agree with each other.
Oh,
For many medical diagnoses, it's not 1, it's not 0.9. It's like 0.3s or 0.2s.
yeah,
I'm gonna bet for your task. If I say, here's a specification, spend 3 weeks and get me your best answer. Team 1 will have this one, and team 2 will have that one, and not the same.
yeah.
Even if I would say, here are 2 different layouts, tell me which one's better. Even that simpler test, I bet there would not be a University of Alberta. So what are you trying to do? You're trying to match this expert, that expert. Why aren't you trying to find the best thing? It's some predefined notion that says this is what best means.
Yeah, I agree with that. So since in chip domains, when I talk to those chip engineers, so they also ask, so they also explain that. So in chip domain, when they design the chips, they also require lots of iterations to talk with the customers. So because there are so many metric over there, so maybe something metric this thing too for chip engineers isn't good, but it's not match the standard for the customers they want. So yeah, it's just like you said, it's hard to.
Customers can't articulate it. I guess you're saying there's no articulation. You have to just try, just a try and error. And eventually, this customer doesn't want it, but that customer will. And you're happy with that? That chip manufacturer happy with that?
I think this would happen that. So just like maybe there are so many possible solutions, who could be the manufacturers, but yeah, I have no clear answer for this one. Yeah.
We've done a CAPA test, we're saying, have 10 different world-class expert in chip design and say, for everyone, then here's the chip design one, here's chip design two, but same purpose. Which one's better? And he has 10 experts and say, that they agree on these 30 different trials. Do you think CAPA is one?
I don't know how the chip engineer do in the real world, how do they make the decisions for which one is the best? So yeah, sorry, I don't know how to answer these questions.
Like, isn't it somewhat easy? You just have you have like 10 softwares, a suite of software that you will run on your chip. You just run them, and whoever is your biggest customer, you design chips for that. Like that happens with t-shirts as well.
Customer, 3 different experts.
No, customers are not experts, right? Okay, if they're experts, you just pick the biggest expert, or if you have the
Whoever
capacity,
gives
you
you
run
most money.
3
I-
different.
I think the problem for them is they really need something fast speed iterations to generate something, the new floor plan. So once they changing something preference or maybe it's just like a Peruto preference. So for chip engineers, their jobs is as fast as possible to generate the solutions.
Yes.
Yeah, right. So maybe like the customer or something. Right.
Because getting a solution quickly, that's easy. Drop the trips that ran, done. Oh, you went to work also. Okay, that's.
Yeah, maybe a related question. So you said there's like a real metric from the EDA tool. What is that?
Okay, so for all the simulators, actually is not, so it's more like the proximity to simulate, so everything down, so including, we maybe go to the really beginning for this graph. I'm not sure, can you clearly see the words in here? So there's something, the floor planning, placement, routings. So some metrics so like the real map performance, you cannot get after you finishing the whole procedures. And that's the commercial EDA tool is for running the whole procedures before the manufacturers. So they will get the real performance. But for simulators, they can get something approximated rewards. So after only the placement results or only the routing results. So it will be the shorter, will be faster iterated. Yeah.
Okay, and I just follow, these are just, each of these are just like certain metrics that are associated with each, so it's not like all the metrics, I guess.
I think all the metrics are the approximated.
Okay.
Yeah. Okay.
I think you mentioned that usually the first method, they all care about the final design of the chip. And rather than the intermediate step, like how I iterate the numbers or not.
Right.
But one thing I'm really concerned about, I think I'm not covering the Chinese test, was whether the result is extendable or not. For example, if I provide the design chip to an engineer, and maybe the engineer, I can find out like this block, why is block here, or why this block at that corner, and the engineer makes them like because it's need more some matrix and this block actually quite different. They're not the same block. And I'm not sure whether that would be the same case in this chip design domain, like you just need to care about the result, or you have to make the process extendable so the customer or this EDA expert can really follow the result, or to extend whether the result is good or not, just not only just beyond the result.
I think that's also another good point. So you're pointing out another valuable research direction for this chip domain. So for chip engineers, they also using their own heuristic experience. They also have no idea why is this block putting here, why not that block putting over there. So if if the AI agents can tell something reason or give something explanations of their decisions, that will be another great work for the EDA domain. So maybe tell the EDA experts, so why they make these decisions, just like the AlphaGo, so they can teach the humans to how to make decisions to play the Go.
Can humans do a good job of explaining why they make their decisions?
Sorry,
Can humans do a good job of explaining why they made their decision? Why you put the chip there and not there? Are humans good at that task?
no, so
Is that like,
so the
bunch of games?
yes. Yeah, so sometimes they're just using their own heuristic experience.
It's perfect, right?
Yeah, so that's perfect for us to make it better. Cool, okay.
Maybe another question. So, you mentioned that in the Google Works, it was like I think a much smaller board, like maybe, I don't know, 10 by 10, 100 by 100, just let's say it was smaller.
Okay,
But then like a real, I think you also said like a real chip
Yeah.
board is like
yeah, over the
crap
top,
ton
yeah.
bigger. So is the Google chip placement, I think this is kind of what maybe what Russ was asking earlier. Would that not be a real chip? Like, is that a real, like, can you not,
Yeah,
if it's not
so,
really the size of the chips that are actually used in computers, then it's not like, they didn't,
Yeah,
yeah,
so-
it's not one that could now be like,
I,
run my computer.
yeah, right, so that's why there's so many critics over there, so to judge the Google's work. So by Google's team, so in their Nature's paper, so they playing around 100 blocks. But so because no one know what's the real design of the TPU. So no one know what's the real number of how many blocks in the TPU. So yeah, so this will be the unknown answers. Yeah. Okay.
So what kind of network architecture do you use? Is it like a convolutional network?
Yes. So for Google's network, so they're mainly using the graph convolutional neural networks. Yeah, so because the input will be the that with the graph. So yeah, so the constructed state as the graph formations. But for in here, so there is something folding up words. So maybe like this one, marketplace. So they're not using the graph neural network anymore. So they don't using they don't construct the state space as the graph informations. Instead, they pure using the convolutional neural networks. So the construct state space at the 2D chip canvas. So it depends on how do you construct the state space.
So I thought the graph would be a 2D grid.
Yeah, so so they have so that's the whole papers are talking about. So they mention the new presentations. Yeah, so representations about the state space.
And what? Sorry, go ahead.
It's playing devil's advocate. The whole field of inverse reinforcement. See what extra does and try to match with that extra doing. As a whole community would hit this area. I'm not a big advocate of it. Has someone tried this idea?
Try what idea?
Inverse reinforcement.
Oh, reinforcement?
Inverse
In
That's, you observe what people do, is let me figure the reward function they must have been using to produce this. So you just observe people acting in a way, which is obviously
Oh.
optimal, people are optimal. And you then try to say, they're optimizing some function, that function is obviously this one.
Yeah.
It's a bad idea, but someone tried this.
that's the thing. So we don't have that the expert human engineer.
You have experts who design chips,
We don't have. So maybe just the companies they have, but
you don't make it public.
yeah, that's the thing. So we may never know would they would do the things if they have the experts, so they can do something imitation learning like
Yeah,
so but that things it requires the experts trajectories, but we don't have. So I'm not sure all those the EDA companies would they do this the same thing? Yeah, like you said.
again, I'm not advocating, that's true.
No, that's a really, yeah, that's a great point. Good point.
What kind of algorithms are nice to deal with sparse rewards like 0, 0 everywhere and in the end you get some reward.
Yeah, actually, so they just,
I guess some algorithms might be better. For instance, if you're just relying on local information, what are you doing that you get?
could you say the questions again?
Oh, I don't, I'm thinking.
That's good. This is like discussion sessions, so it have to be asked.
If you have very sparse reward, like maybe as you were saying, as well, like, are there certain algorithms which are better than others?
So I think there's only one to try to using R&D as the intermediary word to solve the sparse reward settings. So for others, majority is still using the sparse reward settings. So just
But what methods? What,
oh, they're just using PPO. So just PPO to train the agents.
I thought policy gradient methods would be the worst and I don't,
Yeah, so maybe that's the one of the reason why everyone cannot reproduce the rules results.
Or maybe they.
Yeah, go ahead.
So have you mentioned any reason about why they specifically chose sparse reward setting and not, because they could have gone for a dense reward, I guess. It wasn't like a big design decision, would have been a big design decision for them. So did they mention any specific reason for going for sparse reward in the paper?
So because they construct the problem as just the MDP, so placing block one by one. So this automatically bring the sparse reward settings. So I did not specifically why they using this sparse reward setting, and I also don't know why they not notice that. So we are the first right now. Until right now, we are the first to propose the swapping MDP to change the sparse reward to dense reward settings.
you blew up your actions.
Yeah, we changed the action space. Oh, the grew up. Will be the group expand. Yeah, it will be expand, but we're also using some tricks to narrow the action space. Okay.
Very different. I mean, you
Okay. I understand why reinforcement is not really good choice for certain part. Oh, hi Masa. So I now see the reinforcement learning is the good choice in here. So I just want, so in here, that's why I mentioned, so I leaving as the open discussions. So this is the one of the problems or limitations of the current work limitations. So they just modeling this problem as the single objective, but actually the real world engineers don't hear this the single objective optimizations. Yeah, so it's maybe there's a better way to solve these problems.
But I guess whatever works, we then call it reinforcement learning.
What?
I see, AI driven, so.
Okay, so that's it. Thanks everyone.